Hello, everyone, and thank you for joining us today. My name is Sean Sullivan, and I will be your host for this NASA Technology Transfer Program webinar on the Universal Wireless Flight Sensor Systems technology. Our presenter today is Matt Walderson. Matt is a research and development engineer at NASA's Neil A. Armstrong Flight Research Center. After receiving a BS in electrical engineering from Purdue University in 2013, he worked as a design and research engineer within Orbital ATK's, now Northrop Grumman, propulsion system division. While at Orbital ATK, his primary areas of focus included flight instrumentation, avionics, and electrical ground support systems for the Space Launch System solid rocket boosters and the Orion spacecraft launch abort system. He was also an integral member of various research and development teams at Orbital ATK, conducting research into advanced avionic and instrumentation systems. In December 2015, he began his career at NASA, where he works as a researcher in the Flight Instrumentation and System Integration branch. In his current position, he has been part of the Orion AA-2 instrumentation team and the X-59 low boom flight demonstrator instrumentation team, and is currently the deputy flight systems lead for the F-15D supersonic research testbed. Today, we will focus on the technology developed to incorporate wireless sensor technology in aerospace vehicles without adding the complexity and tonnage normally associated with physically modifying existing avionics. A single universal wireless access point or gateway that can communicate between existing onboard systems and any subscribed wireless device. Following today's presentation on the wireless flight sensor system, I will give a short presentation on how NASA licenses technology to outside organizations. Now, before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box and we'll answer them during the Q&A session at the end. So at this point, I'm going to turn it over to you, Matt.
All right. All right. Hey, so really quickly, my name is Matt Walderson. Thank you, Sean, for introducing me. So let's get right into it. So what problem are we trying to solve? Why do we need wireless sensing on an aircraft? And it turns out that cables are really, really heavy. So this is some figures I got off the New York Times. But the Airbus A380 has over approximately 100,000 individual wires, which accumulatively add up to 300 miles in total length and 12,500 pounds in total weight, which is pretty ridiculous if you think about it. Like, I think an elephant weighs like 2,000 pounds or something like that. So that's roughly 6 elephants just in wire hanging out on an airplane every time it takes off. So there's the weight savings, but a lot of things that people don't realize is they're also really difficult to integrate. You need a team of engineers like me that are designing where to put it, where to route it through. You need mechanical designers. That means that you've got drawings. That means you've got, fleets of technicians that are trying to route things through. There's procurement. And all of this is non-recurring. So there's not only a loss to payload, but there's also, it's expensive to actually design into your system, all of which is non-recurring. So you don't get any return off of investment basically after you do that. So if wires are such a big issue, why don't we have wireless avionics systems? And when I first started here, that was something that we really kind of took a critical look at. The most obvious reason, which it sounds kind of silly when you think about it, but it's actually a pretty big issue, is that current avionics systems don't support wireless technology. There's a high cost in replacing pre-existing avionics systems, which basically means once you wire something up and once you've designed it, you need to pay those same designers to unintegrate the system that you already have. So pre-existing wired systems aren't just going to magically disappear. Also, there's a lot of regulatory compliance complexities, which means, we've got the FAA in the US, but, airplanes fly over the world. So you may have regulations in one part of the world that are different than somewhere else. Also, with the emergence of portable electronic devices like your cell phones and your laptops, the FAA, their policy is, evolved over time. So at the time when I put this presentation together, I think it had evolved 5 times since 2000. It used to be that you couldn't use anything wireless, and now it's okay, just wait until you get to altitude and you can use your phones and everything else. So that's evolved over time. Another major barrier to wireless avionics is obsolescence risk, right? So why would I design a flight system that can incorporate newer or alternative wireless technology several years from now? And I think that this graph does a good job of kind of just showing how quickly things are advancing. So if you were to design, a wireless system that utilizes Wi-Fi in 2009, your data rate is roughly, 450, megabits per second. And then 3 years later, it's already gone up, by a factor of three. So you could have had the latest and greatest cutting edge technology back in 2009, but within 3 years, which is well within the lifespan of the vehicle, you've already got a system that's way obsolete. The other major barrier that we saw to wireless avionics is there really isn't a one size fits all solution. So each wireless communication method has its pros and cons. So for example, Wi-Fi, which is 802.11, is great for high bandwidth applications. You can get a lot of data through really quickly, but it also utilizes a lot of power. Where take like Bluetooth or RFID, super low power. In fact, RFID is basically zero power. But you can't get the transmission rates that you need um, with that technology. So, some applications, Wi-Fi is probably a little bit better. Some applications, Bluetooth, RFID would be a little bit better. So the optimal wireless avionics system needs to be heterogeneous. So one thing I want to point out when I'm talking about barriers to wireless technology, there are other barriers, like in certain environments, there's shadowing, reflections, you can't transmit through metal, there's time synchronization. But the point of this, technology that we're working on is really the avionics interface to incorporate these systems. So with that in mind, what are our goals and objectives? What are we trying to solve? So we wanted to design an avionics interface that lessens the challenge of integrating new wireless systems. So that goes into the whole obsolescence risk thing. And it also, ties into, easing the integration risk. So we wanted to design a wireless avionics interface that could rapidly incorporate new wireless technology. So we want to be able to choose the right wireless technology for the right application, reduce obsolescence risk again. We wanted to design a interface that was implementation agnostic. So, right now I'm working on an F-15. That's the supersonic research test bed. If I designed this wireless system that could only work on an F-15, it's not really going to do a whole bunch. Um, and we also wanted to design, and this is one of the things that I've come to realize more and more, is we wanted an avionics interface that provided a layer of abstraction. So basically what that means is you've got a lot of really smart wireless communication RF engineers out there. But not all of them know a whole bunch about, integration, like avionics integration and flight instrumentation and that sort of thing. And then conversely, you've got a lot of people who know a lot about instrumentation and avionics, but they really don't know how to design wireless systems. So we want to achieve something called technological convergence, where we've got, one field that's rapidly advancing, and we want to be able to merge those innovations into an avionics platform. And in order to do so, you need to design it so if you're a wireless designer, you don't really need to worry about how the data is being used and what's, happening there. You want to be able to just have two separate systems where you're like, okay, it goes to this point and you can communicate, there's no issues. So to give you an overview of our current work is we're currently designing a wireless flight system, wireless flight sensor system that leverages software-defined radio technology. And I'll go into detail on what that is in some following slides, but basically the benefit of a software-defined radio is that you can incorporate new wireless capability entirely through software modifications. So this addresses, the issue where it's like, okay, if you had a wireless interface, every single time a new technology comes out, you need to install a new interface for it to work. So what's great about this is that gives us the ability to rapidly incorporate, other people who are doing flight test experiments with wireless avionics without needing to modify our pre-existing avionics architecture over and over again every single time a new experiment comes out. So again, the point of this technology really isn't to introduce new, wireless protocols or modulation techniques or anything like that, but it really is to facilitate the technology and the development and the work of others. So, what is software-defined radio? Um, I think this image on the right does a good job of describing that. So, if you look at like all the different things, you've got multiplexers, modems, digital tuners, all the stuff. Those are the different parts that go into wireless communication. Now, if you look at the graph that says hardware radio, you can see what amount of all the things that are required in wireless communication. All of this is being implemented on designated hardware. So, if you wanted to use a Wi-Fi communication, you would need a Wi-Fi chip. Bluetooth would need a Bluetooth chip. But with software-defined radio, it takes all these things that are traditionally done in hardware and it implements them in software. So with that, we're able to, communicate with a wide variety of frequencies. And we use the phrase, adding wireless capability at the speed of software. And this is why, is because we don't need to add new hardware every time we want to include a new wireless technology. So again, it's reprogrammable to accommodate a wide variety of current and future protocols. That goes into the obsolescence risk issue. And it's ideal, at least from our center's perspective, for testing and developing new wireless sensor technology. So to kind of really hit this home, I want to propose a use case scenario. So this is if we wanted to install some type of wireless thing on an airplane right now, and this is how it would basically go if we didn't use software-defined radio. So let's say we've got the system that uses wireless sensors and they communicate over Wi-Fi. And then some new cutting edge sensor technology, but it uses Bluetooth comes out. And we really want this Bluetooth technology on our airplane. So if we wanted to do that, we'd have to, modify the pre-existing Wi-Fi system to incorporate both Wi-Fi and Bluetooth. Which even though, yeah, we're leveraging wireless technology, we're still running into that reoccurring engineering cost. You need engineers to design and route power to that new access points. You need to flight certify it. And even though you're saving wire, you're still inheriting a large amount of integration cost. So let's look at the same situation though with software-defined radio. So again, you've got this Wi-Fi sensor system on your airplane and this new cutting-edge, awesome Bluetooth technology comes out. Well, at first, you're kind of in the same situation where you don't have a Bluetooth compatible interface. But with software-defined radio, all you need to do is upload the new Bluetooth communication protocol onto this access point. So you don't need to go through and remodify, integrate new interfaces, check that out, test that out. So you're able, again, to integrate new capability all through the speed of software rather than the speed of hardware. So how this architecture works, we utilize something called a publish-subscribe architecture, where publishers are things providing information, subscribers. In this image, I call them flight computers, but it really could be anything. I know that people doing flight critical avionics, they're like, okay, hold on, we're not quite ready for that yet. But if you're doing low criticality flight test instrumentation, developmental flight instrumentation, or if you just want to even use it for things like, the button you press when you want to call a flight attendant over, or like smoke alarms and stuff like that. So basically, in this architecture, the software-defined radio access point acts as a broker, which is basically something that takes information in and then gives it out. So you've got the publishers, which are the wireless sensors, which are things, think of it like a newspaper, that are providing data to this access point. They don't know what it's being used for, where it's going. All they care about is, okay, I need to provide this data to this access point at this time. And then before a flight, you've got the subscribers, which are things that are requesting information. So what the subscribers do is they go to this access point, they're like, hey, I need this information at this time. So there's no direct connection between wireless sensor and the flight system. Both of them are only communicating to this one access point, and there's an air gap between the two. And the software-defined radio, again, as this broker, takes the information in, and it's like, okay, I'm getting this stuff from these sensors. and it now needs to go to these points at these points in times. So you don't need to worry about routing through the flight network or doing anything like that. So if you look at this architecture, so what are the advantages of doing so? So, okay, we want to eliminate the need to constantly integrate new hardware. And the software-defined radio as a universal access point really solves that problem, because all you need to do is, again, modify the software, which makes it, rapidly reconfigurable. Again, through the speed of software, you don't need to worry about installing and integrating new hardware interfaces. It's implementation agnostic. The access point really just serves as a courier of information on a pre-existing vehicle network. So you can put that on, an airplane, but it can also go onto like a car or in a factory or in agriculture. And it provides this layer of abstraction that we were looking for. Because again, if you're developing a wireless sensor, all you need to worry about is communicating to this access point. You don't need to know how the data is being used, how it's being formatted, where is it going, and vice versa. So you just link up your, quote unquote flight computers to this one access point, and you don't need to change it, how that system works every single time you want to incorporate a new wireless technology. All you need to do is subscribe to that information. The other advantage, and this is one of the cool things, a lot of people look at this and they're like, okay, the software sounds really great, but I don't know how to design a software-defined radio. But what's awesome about that is this hardware platform already exists. This isn't a new technology. We're just repurposing it. They're used for electronic warfare, and they're just used for wireless research in general. When we get into the current state of the technology, I've got a software-defined radio at my desk right now. So there's no, again, another benefit, one of the questions I get a lot is cybersecurity. And yeah, there's no hack-proof system. I mean, you can always, flood the RF spectrum so nothing can communicate. People have brought up, oh, well, what do we need to encrypt the data? And for me, that's really up to the user. But it is intrinsically safe from a vehicle standpoint, in the sense that the only way someone would be able to access the information being provided and knowing how it's used is if they somehow got into the vehicle network and subscribed to it. This becomes a little bit more of a problem when you get into things like agriculture and systems where it's easier to have access to what you're subscribing to. That's referred to a man-in-the-middle attack. But again, you do have this air gap where you don't have the ability as a, external wireless device to communicate directly with something on your vehicle network. And it's also a modular architecture in the sense that, you upload new apps or what have you, and that gives you the ability to integrate new wireless communication capability. So, yeah, like we're NASA, and I talk about how, cable weight is, something we're trying to cut down on, but this isn't limited to the aerospace and defense. Basically, anywhere there's a need to reduce wiring, or wiring isn't practical and wireless sensing is something that, would work, this architecture would fit. So again, I mean, manufacturing and industrial facilities, think about all the wiring and all the stuff you need to put into an assembly line. Automobiles, infrastructure is a big one. Agriculture, you can't route, wires into a field, and have that, be practical. Logistics and distribution facilities, smart homes. Again, anywhere there's a need for wireless sensing, this concept could be put to use. So a lot of times someone will come up with an idea and they're like, oh yeah, this is a cool thing. So it's cool, therefore you can go and sell it. Where in this case, again, it's really contingent upon incorporating the technologies of others. So we wanted to take a moment and talk about the business models that someone who would be interested in licensing this technology could utilize. So the first obvious one, right, is a marketplace business model. Growing up, and I think that this analogy fits, to me, what made a smartphone, it wasn't the touch screen, it wasn't, like the camera, it was the app store. Because if you think about it, before smartphones, if you wanted a phone that did a specific thing, you would buy a camera phone or an MP3 player phone. One of my friends growing up wanted an ESPN phone really bad because it would just text him the scores of, like the Cubs and the Bears and everything. Um, then, so you had a hardware centric solution and you didn't have like, if you wanted a certain capability, you would need to buy specific hardware in order to get that capability. And then the smartphone comes out and it's got this modular architecture where it could be completely user definable. And they use this marketplace business model where it actually made it more profitable by making it user definable and making your customer happier. So in this case, yeah, if you've got a universal platform that can basically communicate with any wireless device. So you can have these software modules being developed by third parties and then resell that in a marketplace. You can sell wireless sensors in a marketplace. I think a marketplace business model would be really applicable here. The other one is the razor and blades business model. So the definition of that, right, is one item is sold at a premium in order to increase the sales of a complementary good or service. So when I first heard about this, I was actually a kid. So my dad was an investment banker when I was growing up, and he was telling me a story how someone came up to him and they were trying to sell oil that you could put on to like extend the life of razor blades. And he mentioned that that was like the holy grail of like a business model. And my dad asked him, well, how do I know it just isn't baby oil? And then the guy got super mad and left, and it turned out it was baby oil. But it always kind of stuck with me. Why is extending the life of razor blades a big deal? But the origin of this business model, it started when razor companies like Gillette would give away razors for free. And that seems like a weird way to make money, if you're giving away your razors for free. It turns out if people liked them, the margins were so high on replacement blades that they would make back the money that they made, just even though they were giving away their initial product for free. And that's actually something that's seen in other industries as well. It's my understanding that gaming consoles, they actually lose money every time they sell a console. And that's because if you think about it, okay, you lose $100, but then you can't do anything with the gaming console unless you either download apps or you buy a video game. And the margins on the apps and the video games are so high that they make their money back, instantly. So, this gateway by itself, it needs other products, complementary goods and services in order to be useful. So if you're looking to, use this marketplace, expand that out, you've got a product that in the act of having someone buying it automatically will automatically result in the sales of complementary goods and services. And then the final one is, a subscription service. So anywhere there's a software architecture that involves things like apps, you can charge for someone to, have access to this. You can have subscriptions to, the wireless communication modules, as well as just the architecture in general. So the current status of it, the crux of the technology is having this one piece of hardware that can be reprogrammed to communicate with a variety of wireless devices. So that includes not only dissimilar protocols, but also different communication frequencies. So we were able to show in the lab, yeah, you can absolutely have multiple wireless devices, and with minimal software updates, or modifications, you can easily reprogram it in a modular way to communicate with a variety of devices. So with that said, an initial version of the software with this publish subscribe architecture and everything is in development. But we're kind of stuck between a rock and a hard place because on one hand, it goes back to what business model you want to adopt. So if you want a subscription service, if NASA is going to be developing software, we're not a business. So we're not going to include, a subscription service in our initial version of the software. There's also, okay, well, what industry do you want to apply, have it work with? If you want to go the aerospace route, yeah, like, okay, you're designing it for a ruggedized platform, that's aerospace approved. Well, if you're trying to do this for agriculture, I mean, then that's kind of overkill. and that's a pretty expensive access point. And since the architecture itself is dependent on what hardware you use, we're realizing that, okay, even if we did have, this beta version available, ultimately we couldn't just give it to someone and have them move forward and, instantly put it to use um, without incorporating their business model. So what the ideal situation for us is that we're able to license this and basically buy it from whoever decides to manufacture it. So again, it depends on what software-defined radio is being used, what type of business model you want to incorporate. Is there going to be an app store interface that we need to work with? All that stuff is beyond the scope of a NASA development project. So we'd like to, give that to you guys basically. So with all that said, that's the presentation. So are there any questions, discussions we'd like to have, or?
Well, thanks, Matt. Real quick before we get into the Q&A, I'm going to go over a couple of slides on how businesses can partner with NASA through technology licenses. So if you can go ahead and just go to the next slide for me. So as with the technologies that we discussed today, NASA has approximately 1,200 other technologies in a variety of categories available for licensing. These technologies are listed on our NASA Technology Transfer portal at technology.nasa.gov. Additionally, NASA has hundreds of downloadable software programs available for use through our NASA software catalog at software.nasa.gov. New technologies and software are added throughout the year across the agency, providing the opportunity to a variety of industries to access NASA-developed technology. Next slide, please. So on the Tech Transfer portal, the technology.nasa.gov website, each technology has a page that provides an overview and has a link to take you directly to our automated license application process. Once an application has been received, the licensing manager will review the application and reach out to you to discuss next steps. So for this particular technology, you can see the web link that's there at the bottom where you can go in. There's also a button that allows you to just ask questions if you don't want to get directly into the licensing application process. Next slide, please. All right. So additionally, there's a lot of other resources and information about our program, how it works on the website. If you want to learn more about the technology licensing process, you can go to technology.nasa.gov/license. But if you have any specific questions, especially about this technology or the presentation that you saw today, please contact the Tech Transfer Office at NASA Armstrong using the email address that's right there on the left side of the screen. Once again, we really appreciate you taking time to be with us today, and hopefully we'll see you at another upcoming NASA Technology Transfer webinar. You all have a great day.